Hi, and welcome to Introductory Algebra-Based Mechanics. In this course, we will be taking a look primarily at the motion and interaction of objects. To start out, I will start by defining the subject of physics, and I'll define it as the study of the basic components of the universe and their interactions. Okay, so what do we mean by some of that? Let's start with what I mean by basic components. It seems like components. So here we're talking about the building blocks of matter. And we're still not entirely clear on what those building blocks are, but we have some clues. Oops. So, for instance, you've probably heard that atoms make up molecules, which in turn make up larger objects like, say, the cells in your body, which in turn make up physicists who worry about stuff like this. But it turns out that these things are themselves made of stuff, and we're trying to figure out how far down the rabbit hole that goes. So, for instance, we know that the atom has some structure. It's made up of a nucleus. And it also has some electrons orbiting the nucleus. Now, as near as we can tell, you can't break an electron into anything smaller. And it seems to be one of 6 particles that belong to a family of things called leptons. Okay. Now, within the nucleus, you've probably heard that the nucleus gets made of objects like protons and neutrons. So those are smaller components to the nucleus. And those protons and neutrons, it turns out, get made of even smaller objects that are called quarks. I wish I could say that the word quark was named after the German word for yogurt cheese. It's not. It's actually in reference to a line in James Joyce's novel Finnegan's Wake. But in any event, it turns out that there are 6 of these quarks, and 2 of them, what are called the up and down quark, in different combinations of 3 of them, make up the protons and the neutrons. Now there are open questions as to does this stop at quarks and leptons? Does it go even smaller? That's a field of active research. For instance, people working on things like string theory are exploring exactly that. Now, it turns out that at each of these distance scales, the objects interact primarily through different forces. So, for instance, at the distance of the region of the really small, the strong nuclear force holds sway, and the quarks will interact with each other via the strong nuclear force. When we get to a little bigger scale, say up to like atoms and molecules, here it's the electromagnetic aspect of what gets called the electroweak force. So we'll say electromagnetic here just to be clear. That dominates. It turns out that the protons in the nucleus interact with the electrons that are orbiting the atom via mostly the electric aspect of the electromagnetic force. Now, it turns out that if you look at your typical atom, you always have just as many protons as electrons. So you always have just as much positive charge as negative. So once you get a decent distance away from an atom, such that you can't really tell that there's something orbiting anymore, then it just kind of looks like a charge of 0. And the electric force, although not totally gone by any stretch, starts to diminish in importance. And something similar happens with the strong nuclear force as you zoom out from the nucleus. So it turns out that when you get to long ranges, like when you get to, say, physics instructors interacting with planets or something like that, the weakest of the forces of nature, gravity, is about the only player left in town. Now, in this course, we're going to be the two forces that we'll mostly be focusing on will be gravity, and we'll also deal with the electric force to some extent in our models of things like friction and tension and stuff like that. Okay. So it also turns out that some of the things that we deal with in physics are things that we're still working on trying to describe thoroughly what it is. So let me just start with a bit of a thought exercise here. I want you to think about what is time. Go ahead and pause the video for a little bit and then come back with what your thoughts are on it. Okay, so probably you were having some challenges with that, and that's okay, because it turns out that the physics community doesn't really have any clue what time is at some deep fundamental level either. So how can we talk about it consistently? It turns out to do that, we use what are called operational definitions. So, for instance, for our definition of time, so if we ask what is time, the response that a physicist should give you is that thing that a clock measures. Now that may seem incredibly cheesy and somewhat disappointing, but really we don't have any better clue. If you read Newton's Principia, the foundation of material of this course, Newton goes on for quite a while describing time and then basically ends it by saying, "Oh, come on, you know what I mean." And that's been the problem we have, is we really don't know what time is. That's an open research question. One of the great breakthroughs of early 20th century physics was that we found out that it is somehow intertwined with space. And yeah, that's about as far as we've gotten with it. So we need to be able to consistently agree on what we mean by time, and we can say, well, we can recognize it by having a consistent recipe for how to measure it. So for instance, if we want to talk about an operational definition for elapsed time, you might give a step-by-step recipe that looks like this. Step 1, set timer to 0. Step 2, turn timer on when event starts. Step 3, turn the timer off when the event stops. And then step 4, read the value on the display. And when you get right down to it, that's all we need to be able to consistently agree on discussing time. We can all say that time is what we get when we use a clock to perform this sort of measurement. Someday we'll be able to figure out at some deeper, more fundamental level, we hope, what time is in some deep, more fundamental sense. But for now, this is going to be what we'll have to use. It turns out that when we get down to it, there are a grand total of 7 quantities, 7 things that we have to define operationally. We call these the base quantities. So that includes things like an object's mass, its length, time, like we've already mentioned. Temperature is another one. Those are mostly the ones we'll worry about in this class. There will be electric current in the next course. Luminous intensity, sort of. And again, in this course, we will get back with the amount of a substance. So these are the things that we have to define operationally. And then it turns out that everything else, what we call the derived quantities, we can scaffold off from that. Okay, in the next video in this series, I will spend a little bit of time talking about units. Catch you in the next video.